Okay, so I'm going to be talking about math as it applies to my favorite thing, physics, especially in space. I love space. So basically, I already have it written there, but I'm going to start make myself bigger. I'm going to start by talking about Newton's laws, Newton's first law, as he exactly, well, I need to open it because I don't have it exactly memorized, but as he states, the alteration of motion is ever proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. That was understood by the scientific community to be force is equal to a change in momentum. Momentum is just basically movement, but it's velocity in a given direction. So force equals dp over dt. You can think in calculus terms. It's the rate of change in momentum. Momentum, again, we have p. That's momentum. It's always p. Don't put m because m comes up a lot later, and you need to save m. There's some more important things. So p equals mv. And we also have force, which is the thing we need. Equals. We're trying to get that great equation F equals ma because he didn't just say force is mass times acceleration. He made other people do that work for he probably did it himself, but he had to save something for us to do. F equals dp over dt. Ugly math. We know we can substitute that mv in for p. So we get F. I'm rewriting it because it's easier this way. F equals m dv over dt. Great. Well, in calc we learn one great thing is that the change in velocity, because that's really the only thing in this equation that can change. Yes, you can change the mass, but that's the most variable thing, and the mass changing is more accounted for by the equation. Why we have so we get F equals ma, because the change in velocity is also known as something wonderful called the acceleration. That equation is, again, very well known, very well respected in the scientific community. It's a personal favorite of mine because every time I try to do anything physics related, it shows up again. Like Newton's third law, every action has an equal opposite reaction. Okay, yeah, it's there, but you don't see it. Inertia, you see it sometimes, maybe not others. Because motion is things are moving, forces are happening, so everything is being acted on by an outside force. Everything, because gravity is everywhere. Go to the screen. So we have F equals ma. It's nicely written, so I don't have to write that again. So we're going to talk about gravity, because gravity is everywhere. It's just there's this not as present everywhere. I am gravitationally affected by a random star. A random moon in the middle of the Andromeda galaxy is pulling on me, but Earth is pulling a little bit harder, so Earth is winning that battle. And the sun is winning the battle with Earth. Not necessarily because of size. That is a factor, but there's several factors. Gravity, F of G. So that's written. F of G, force of gravity, is equal to the gravitational constant times the big mass times the little mass. This is the mass. This is the mass that's in theory being pulled in. Granted, both things are pulling on each other. This is Newton's third law showed up. Every action has an equal opposite reaction. They're both pulling on each other the same. But also because of this equation, they are pulling on each other the same. The force of gravity is the same for both objects. But we usually use m for the larger object because it has the greatest gravitational strength. And that's over r squared. R is the distance. That's why something so far away has an effect on me, but it really doesn't, because that star, maybe this giant supermassive black hole at the center of the Andromeda Galaxy, it's way bigger than the Earth, but it doesn't pull on me because it is so far away. It'd basically be like taking the limit of this as it approached infinity. You're gonna get basically zero because it's infinite distance away. That's great application of limits. But I'm gonna tell you, like, with this, we have this value we use on Earth, 9.8 meters per second squared, in my physics class. I used 10. Did not like using 10 because it is 9.81. I used 9.81. One test, I used it, I got it wrong, but I was so mad. But it is 9.81. But that value comes from the assumption that we are at the equator. We obviously move about Earth. So our distance from the center of gravity, it's a very important thing. Center of gravity is very important in all of this. Is changing. It's not going to vary that much because it's not like we're like moving a lot. If you're at the poles, it's going to be different than you're at the equator, obviously. And also the center of gravity is constantly moving because the center of Earth is liquid. So it's going to be all slushy, moving around. I don't know what goes on down there. That's more of an earth science thing. But when you plug things into this equation, you have to make sure they are in SI units, because to do math in physics, to do math in any science, you need to do it in the right units. You need to make sure you have the right units. G is going to be newtons times meters over kilograms squared. It's going to be a really weird unit. But generally, if you're giving a distance, you give it in meters in a prop. Like if you're converting between different things, you give the distance in meters, you give your mass in kilograms, you give your force in newtons, and you give time in seconds. There are other things, but for physics, those are the SI units you use, because those are the ones, like, sometimes, like, when you're talking about energy, or not energy, but like work, like a joule, a watt, all of those are like variation forms of like multiple of those SI units put together, and they are those SI units. They're not other SI units. You don't have to do conversions, you just do math. But anyway, I'm going to start by subbing some values that I'm just going to state them because it's really hard to write. So, the gravitational force is known to equal 6.6743 times 10 to the negative 11. So, let's see, really small number, really small number, but it is there. It's very present, and especially if something is massive enough, especially with the Earth's mass, it's going to cancel it out, because the Earth is, this is all in kilograms. The Earth's mass is 5.972 times 10 to the 24th kilograms. So that is a lot. That's why it's big M, because it's bigger than me. I get to be little m. We all get to be little m. And then the radius of Earth is 6.371 times 10 to the 6th meters. And then you square that on the bottom. You plug that all in, and you will get 9.81. Assuming, again, these values are taken from the equator. They're taken from somewhere else. You're going to have some variation in that. But the Earth, like, you're not going to have an extreme amount of variation. It's going to be approximately the same all the time. So then, now we know about gravity. We got to do this thing called orbit, because things that are big, I like to think of it as like the sun, because the sun is the main one. It's the big baddie. Things orbit it. Earth mainly orbits it. Draw it. I might cover it up. But you got the sun, you got Earth. And yep, it's going around. It's having a great time. Going through a full year. We're almost halfway through 2024. It's crazy. But you got it orbiting. So you have this thing called centrifugal force. Now, centrifugal force does not like the orbit. It's like, hell no, I want to go in a straight line. It's basically going to be the force of a tangent line. We learned that in calculus. Any color. It's going to be the tangent line. The item in orbit, pretend that's straight, is going to want to behave like that. It's going to keep going the way it's going because if inertia, Newton's first law, it's going to want to keep going up in the direction that's going, at the velocity it's going. Fortunately, this outside force, this giant thing called the sun, is like, no, we're not doing that. Now, the item naturally does not want to just start moving. It's not going to just move this way and get sucked in and be like, woof, I'm here. Because centrifugal has got a friend named is centripetal. I guess they're related. I don't know. Got the same first name, different last names. Maybe it's like some cultures do that. But she's like, no, we're just centripetal. It's going to be like, no, we're going to go on this little curved path around the thing to kind of balance out the fact that centrifugal's like, yo, no, I don't want to have anything to do with that. But the sun's like, I want to pull you in. And the force that it takes for this object to stay on this line, because it's staying in this motion. Like, it's not moving, it's staying on that path. That's the path it chose. It's going to have to be equal to gravity if it does, because the two forces have to be balanced. They have to cancel out. A little bit of Newton's third law coming in there, a little bit of Newton's first law coming in, because unbound. It is moving. Still, it is orbiting because there is a force acting upon it. But it's not behaving like you think it would. Like, it would just be sucked in. Like, when I jump, I don't just start rotating around Earth at, 2 feet off the ground. I fall back down. Well, this item doesn't, because it's far enough away where it can get into a little battle with the thing it's moving around. Like the moon isn't just going to come crashing in. It's going to stay away because there's that centripetal force that's saying, no, you're going to stay on this curved line. Basically. So those two have to be the same, or else the moon will come crashing into Earth will go crashing into the sun, all that. Forces must be balanced for it to behave the same way, for it to move along that line, doing its little happy thing. So, you got the centripetal force, centripetal, those two. When I write them, I don't mix them up a lot. When I say them, I mix them up a lot. So F of C, which is the important one, that's going to be centripetal. Centrifugal already lost. She's gone. She lost. So her friend came in and was like, no, we're doing this now. That's going to be equal to mv squared, velocity squared, over the radius. And there's going to be some variability in that goes into this thing called an elliptical versus a circular orbit. The radius is going to change, which means the force changes. There's going to be one slightly annoying thing is that, with gravity, that radius changes. It's going to affect gravity a little bit differently because, this R is normal, happy. In F of G, that's the force of gravity, R squared, which is force of gravity equals, it's mgm. I'm like, wait, I didn't write that down. That's because it's this one. It's mgm over R squared. So that squared R is going to make it so that the forces have to be the same at all times, but it's going to make some factors in these equations that are different be a little different. Now, the mass is always going to be the same, because if the moon's orbiting, the moon weighs the same as the moon, no matter what the moon has the same mass. Gotta distinguish those two. The moon has the same mass as the moon, no matter what the moon is moving around. Same mass. So we can, and the forces are equal to each other. So again, we're mostly looking at this acceleration part, this ma part of it. So we have v squared over r, the acceleration, the centripetal acceleration. Oh, I'm going to clear this. V squared over r equals gm over r squared. Now what we want to do is I'm isolating velocity because that's the thing I'm focusing on here. Because honestly, this m and this g are like, not you don't notice it. You're gonna notice a change in velocity, and that's velocity, the scalar quantity. Obviously, if something is moving in a circle, its velocity is constantly changing, or not a circle, an ellipse, but its velocity is constantly changing in the vector aspect of it. But in a scalar aspect of it, it could be staying the same, like when I'm running around a track. Could be going the same, like if I'm running the same speed the whole time, I'm going just as fast the whole time, but I'm moving which direction I'm facing, so my velocity is constantly shifting. Same thing for planets. Honestly, a track is kind of like an ellipse. It's a pretty good example. But this can be simplified to v equals square root of gm over r. And that, if you look at it for a little bit, you can figure out how I did that. I just canceled out part of the bottom and square rooted it. Basically that tells us that as you get closer to the object you are orbiting, you're going to get faster. Like, the item is going to get faster. Like the moon, when it's closer to Earth, it's moving a little bit faster. Thankfully, in terms of the Earth and Sun, same with the same thing. When the Earth is closer to the Sun, it's technically moving faster. But there's not that much variation in the distances on the Earth, so there's not that much variation in the velocity. You can see it, maybe, if you really, really measured it, but a human being is not going to see it from here. In space, you could potentially see it, although it's more difficult because this is all of this right now is relative. When I'm talking about the sun, it's relative to the sun. When I'm talking about the Earth, it's relative to the Earth, because things that are in orbit are also orbiting other things. Like the moon orbits the Earth, which orbits the sun, or which orbits the galaxy, which is just moving around space. So this is all relative to the thing being orbited, because that's the thing that's like causing this shift. But basically, if you're closer to something, you're going to be moving a little bit faster. If you're further away, you're going to be moving less fast. In relationship with it. And I guess this also can explain more, like, if something's infinitely far away, its centrifugal velocity in relation to that thing is going to be unaffected by it, because that r is just so big. Like, so big. Honestly, yeah, you can look at a lot of these, like, it's basically taking a problem and doing limit as r approaches infinity. That's what gravity is. Limit as r approaches this, limit as r approaches that. Like, what is it equal to? Because g and m matter, but in the, like, most variation, because you can't really change, like, when you're thinking scientifically, you can't change the mass of bodies, but you can change how far you are away from them if you need to manipulate these sort of things. So we're going to talk about this v is altered by the distance from the object in orbit. That goes along with this thing called eccentricity. It's a cool thing you learn in pre-calc. I loved it. It was ellipses. Love that unit because it was like new. really new. There's new materials, different. Basically, our orbit. This is really going to be very, very, very exaggerated. No, it's not. It's not that bad. Our orbit looks more like this. Okay, it's more exaggerated now. The sun is not the center. The sun is at a focus point. Focus point is ellipse vocabulary. You should know. There's another focus point that doesn't really. That's a random place that's there. This is again the forces fighting with each other, because when she starts to get, and this is going to remain, because when she starts to get further away, the centrifugal force is like, yo, I want to go on this straight line. And centripetal is like, no, we still have to stay on this curved path. Even though you don't want to, we still got to stay on the curved path. But the distance is approximately the same at all times. Again, this is very exaggerated. But there is a slight variation. Eccentricity is just, again, how circular is it, or how different are the two axes. It's equal to the c value over the a value. There's a major axis, which is the one that both focus points and the center are on. You have your c value. Say this is my center. Your c value is a different distance to the focus point. On Earth, it's going to be 2.5 times 10 to the 6th meters. All of this is times 10 to the 6th. When I show you a graph that I made, it's not times 10 to the 6th because everything is times 10 to the 6th, so it's just scaled down times 10 to the 6th. Your a value is going to be 149.6 something. It's rounded down. I'm just going to say it's rounded down because your b value, which is your b value, which is the this distance, which is, again, the minor axis, is going to be 149.6 rounded up. When I did it on the graph, I did 149.5 because I just wanted to show a little bit of variability, because they're not the same. You basically can plug this into an ellipse equation. I did here. As you can see, I have it centered at 2.5 because I have it because that's where the center of orbit would be. The sun is going to be, in this case, the sun is at the origin. This is just where this thing is centrally moving. This is the center of it. And I have my a and b values plugged in. You can see that it is a lot like a circle, because it basically is a circle, but there is a slight difference. The eccentricity of Earth, the c over a value that I talked about, is going to be approximately 0.017, so it's really, really low. But it is affected by it. The last thing I think I'm going to talk about is a little bit is black holes, because if you talk about gravity, you got to talk about them a little bit. But basically, a black hole, there's an equation. I'm going to quickly check that out before I say something stupid. But basically, a black hole is just a really, really condensed mass. It's something that is... okay. Yes, it's something of any size. Could be any size. This could be a black hole. If it were small enough, it's given by the equation R equals 2gm, big G, big M, over c squared, speed of light. It's a constant, great to have for an equation. Big G is also a constant, so it's great to have for the equation. So basically the mass has got to be, once it's equal to, once you substitute it in that equation, and the radius is equal to that's when it's a black hole. If it's larger in size more volume than that, or the radius, but that's how you determine volume. It's a sphere. Once it's larger, it's not going to be a black hole. Which, basically, if the sun turned into a black hole, things would change, but like in terms of Earth orbiting, would stay exactly the same, because you didn't notice anything about size, volume in that equation, because it's not. Black holes are just really, really like pull things in because they are so big, like volume size-wise. They're like, if their mass was expanded to the density of the sun, they're really dense. That's a good word. But if they were expanded to like normal density, they would just be stars or other planet like objects in space. They would not be black holes. It takes a lot of force to compress it into a black hole. Usually when like things explode, the center of most galaxies, there is a black hole. But no, a black hole is literally just a really, really small star that has the same gravitational field. But it's usually bigger, mass added, so the gravitational field increases with the m value, the mass value, not the size, the mass value. And I think that's all I have to talk about in terms of math, in terms of my equation. Obviously, there is way more applications of physics in real life. Impulse, for one, because impulse, you can integrate your forces to get impulse, impulse is the change in momentum. It's also the integral of the net force from 2 times. So from like starting to time 0 to like 5 seconds, how much the force changed. It's the change in momentum, and momentum is like the change in momentum is also known as the force. So, and there's a lot of other applications of this. There's this thing called angular momentum, which is basically that centripetal and centrifugal force fighting, but that requires very complicated math, a lot of Jacobian matrices, and a lot of like partial integrations or partial derivatives, and long integrations or double integrations or like multivariable integrations. So I didn't want to talk about that because I did look into it. Also more with black holes and gravity. There's obviously string theorem. I didn't want to go into that because that's also more math. But it is all very physics is like math, like science and math married each other, and they had physics, as physics is like the child. So yeah, I think that's all I have to talk about. I feel like I explained it pretty well. I feel like I followed my sheet. And I showed the ellipse of Earth. Anyway, I like this stuff. I could talk. I have no idea how long I've been talking. Hopefully it wasn't too long. But it's math. Physics is math. You just add units. Anyway, how do I cancel?